Today I'm going to talk about power. Now before I can talk about power, I have to talk about work. I love work. I can watch it all day. But in physics, work has a specific definition. Work occurs when you take something and move it some distance using some force. So if I'm digging in my garden and I have a shovel full of dirt, which is definitely something, and I use the force of my muscles to move that dirt somewhere else, I have performed work. In physics, work is measured in a unit called joules, and 1 joule of work occurs when you use 1 Newton of force, which is just under 3.6 ounces. I use 1 Newton of force to move something 1 meter. I have done 1 joule of work. So if I do 1 joule of work in 1 second, and then I continue doing that every second, so I do 1 joule of work in 1 second, another second I do another joule of work, and another second I do another joule of work, I am producing energy at the rate of 1 watt. So watt is a rate. It's 1 joule per second. So as long as I'm doing 1 joule of work per second, I am producing continuously 1 watt of power. It's sort of like miles per hour. If you drive for 1 hour at 100 miles an hour, you will go 100 miles. If you drive at 100 miles an hour another hour, you've gone 200 miles. But have you gone 200 miles per hour? No. You're going 100 miles per hour, and you keep that up every hour you drive 100 miles. So 1 hour is 100 miles, 2 hours is 200 miles, 3 hours is 300 miles, but you're going continuously at 100 miles per hour. Power is the same thing. If I do 1 watt of power for 1 second, I've done a joule of work. If I continue doing that watt for another second, I've done 2 joules of work. If I continue doing that watt for 3 seconds, I've done 3 joules of work. So watt is the continuous factor, such as miles per hour, and joules is the cumulative one. So if I do work at 1 watt, that means every second I'm producing another joule of work. So again, I'm doing 1 watt of power. I do it for 1 second, I've done 1 joule. Do it for 2 seconds, I've done 2 joules. Do it for 3 seconds, I've done 3 joules. But all that time, I'm producing 1 watt of power. So watts is a continuous factor, where joules is a cumulative factor. So power is produced when you have motion. And so if we have mechanical motion, we have power. And when we have mechanical motion on the molecular level, we produce heat. So power produces either mechanical motion or heat, or a combination of the two. And one other thing we may produce with power is electromagnetic radiation. This could be radio waves or light waves, but electromagnetic radiation also is produced when you produce power. So when you produce power, you are either making mechanical motion or electromagnetic radiation. And that mechanical motion on the molecular level produces heat. So in electronics, when we produce power, we have one of 3 things, or a combination of 3 things, either heat, mechanical motion, or electromagnetic radiation. If we don't have one of those things, we do not have power. And I mention that because we can calculate power when there is no power. Let's take a look at the formula we use to calculate power and see how this works. The main formula is power equals voltage times current. Remember, voltage is represented by E, which stands for electromotive force. Some people will use a V here, but that's improper. In proper standard units, voltage is represented by E in formula. So power is equal to voltage times current. And let's take a look at a device where we have voltage and current. This is a transformer. We'll learn about these in alternating current, but just take a quick look at it. A transformer transfers energy through oscillating magnetic fields. So we have alternating current going back and forth in one coil, and that produces a magnetic field that builds and collapses, reverses polarity, builds and collapses. So we have a magnetic field going back and forth across the other coil, which produces voltage in that coil, or produces current in that coil. So we have a transfer of energy across, only when there's alternating current. So we'll talk about these when we talk about alternating current. But one thing interesting about transformers is, although we may have voltage, let's say we have 100 volts here, and let's say we have a current of, how about 10 amps? Let's make this 1 amp. So 100 volts and 1 amp. Volts times current is power. 100 volts times 1 amp equals 100 watts. And if we look at the other side, if this is a step-down transformer, meaning that the number of turns here is 1/10 the number of turns here, so we have a turns ratio of 10 to 1, we would have a step down of voltage. That would be 10 volts on this side, but the current would go up to 10 amps. And notice that 10 times 10 is still 100 watts. However, I'm going to draw a resistor here. We'll need that in a moment. However, transformers do not produce heat except for waste heat from some of the resistance in the wires, but that's undesirable waste heat, and it's only a small amount produced. There might be some mechanical motion because of the magnetic field causing the core to vibrate, but only a tiny bit, and it's waste energy. So transformers do not produce heat significantly, and they do not produce mechanical motion, and they do not produce electromagnetic radiation. So even though I measure a power, 100 volts times 1 amp, gives me 100 watts, there's no power being produced in the transformer except for a small amount of waste energy, which is why transformers are usually specified as volt amps. So the product of volts and current, 100 times 1 is 100 volt amps, 10 times 10 is still 100 volt amps, but there's no power in the transformer. So that's one place where we have a measurement of power, but there's actually no power there. Another place we might see that is in alternating current, especially in motors, but in some other places, we'll talk about this again in alternating current, where we measure a voltage and a current. Let's do this with proper terminology here. We have a certain voltage and we have a certain current, but the power that's being produced is not what we see there, and we have to add a power factor. So we may have what's called apparent power, which is our voltage times our current, but to find our real power, we have to add a power factor, which has to do with some trigonometry, which we're not going to talk about now. We'll talk about that in alternating current. So there are places where our voltage and our current add up to a number, but they don't add up to the power. Once again, in transformers, there's very little power produced, and so the number is basically bogus. In other circuits, we might have an apparent power, which is different from the real power that we have to add a power factor to find out. So that's basically what we have in electronics. When we have power, we have voltage times current, but we don't have power unless we have one of three things produced, either heat, mechanical motion, or electromagnetic radiation. Without one of those, we do not have power being produced. Now, there are some other formulas that we might see. For example, I should have left that up there. That's the main formula, but there's another one. Power also equals our current squared times our resistance. Now we can do some mathemagic and see how this formula actually comes from this formula. You take your resistance and your voltage times your current, and you find out that you do the algebra that it works out to this formula here. But power also equals our current squared times our resistance. So let's go back to our, erased that before I used the resistor, didn't I? So we go back over to here where we had 10 volts and 10 amps. So we have 100 volt amps over here, but no power because no heat, mechanical motion, or electromagnetic radiation is being produced. But over here in the resistor, we have that 10 amps of current plus our 10 volts across it. 10 volts times 10 amps, and we have heat being produced in this resistor. We definitely have watts. There's our 100 watts. It's got to be consumed somewhere, so it's starting over here, 100 volt amps, transfers over to here, another 100 volt amps, and finally somewhere in the circuit our power is consumed or produced, however we want to put that, and that is in the resistor over here. But if we also take our current squared times our resistance, well, what would be our resistance? 10 amps and 10 volts, that would be a 1 ohm resistor. So we have 10 amps and 1 volt. 10 times 10 is 100. That's 10 squared. Gives us 100 times 1, gives us 100 watts. So I squared R, 10 times 10 is 100, times 1 equals 100 watts. Another formula we don't see quite as often, but is sometimes useful, is power is also equal to our voltage squared divided by our resistance. So it depends on what you have on how you calculate your power. So if we have our voltage and our current, we can multiply them together to get our power, but remember when we use this formula, we can sometimes be fooled because we might have a product of voltage and current, but no power being produced, as I explained earlier. In this formula, there's always power produced because resistors produce power. So I squared R gives us a real power calculation. So if you know your resistance, 1 ohm, you know your current, 10 amps, 10 times 10 times 1 equals 100, and that's our actual power. And the same thing here, if you know your voltage and your resistance. Once again, if you have resistance, you have power being produced. So this will give us a true power reading. Take your voltage squared and divide it by your resistance. So here we have voltage squared divided by resistance. And so 10, well, there's our 10 times 10 is 100, divided by 1, that's 100. We still have 100 watts. So any of these three formulas can be used to calculate power, depending on what you know, but just remember this one might not give you the true power. You have to know if your device is actually producing power or producing a apparent power and a real power based on some things in alternating current that we'll talk about later. So that's basically it. Power is the production of heat, electromagnetic radiation, or mechanical motion, and is measured in watts. We use these three formulas to calculate them, and remember that we can use this formula and calculate a power, but we might calculate an apparent power on something that doesn't actually produce power. Now, one more thing I'd like to mention before I go away and all of the stuff I wrote before magically reappears here is that power is cumulative in a circuit. So if I have a circuit, let's say we have a battery and circuitry over here. It goes, I'm just going to draw some jagged lines. We don't know what's out there. But if I have voltage, let's use our 10 volts and our 10 amps. Well, let's just draw that as a arrow. 10 amps. Somewhere in this circuit, we are producing 100 watts, 10 times 10. Now, we may be able to measure the voltage and the current different places, such as if it's an AC circuit, we might measure that at a transformer and it's not real power because power is not being produced. But if we have a transformer, let's even just draw that in here. Of course, we have to have alternating current. Learn about what all that means in the alternating current course. And we have a transformer. And then some circuitry over here doing whatever. There's no power here. But power is being produced somewhere, so it's being transferred over, and somewhere in our circuit we get our 100 watts. So the total power in our circuit can be measured by our voltage and our current. Even though there might be places where we can measure voltage and current where there is no power, if we have our current source and we're measuring a certain voltage from it and see a certain current coming through it, we can be assured that somewhere in that circuit we are producing the power that we measure. So 10 volts, 10 amps, somewhere over here is 100 watts. And that might be a combination of things. Some part of the circuit here might produce some wattage, some other part over here might produce some wattage or whatever, but cumulatively we can measure our total power from the voltage at our source and the current from our source. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.